Okay, so good morning, everyone in Vietnam, and good evening. So hope you guys had a really good vacation holiday in Vietnam. So I'm not sure how whether today we have the full class or not. Let's see, 56, so a little bit less than what we used to, but okay. So today we're gonna do the routing 5, right? So we did the 1, 2, 3. That's introduction, global route, and or the lab, and then detail route. So today, essentially, we're gonna finish with the routing. Um, so after the detail route, what's gonna happen next, right? So similar to the CTS, we have the post optimization step, right? After CTS, and the same thing with the routing. So that's what we're going to look at today. So we look at the overview and what we try to achieve with the post route optimization. Um, so just kind of like reset where we are. So as I mentioned, these are the last step in the routing lecture, the series of lecture that we have. So so I include the VR optimization and antenna fixing a part of this post route optimization as well. So first, why do we need to do the post route optimization, right? So as for the routing, as we mentioned, it's divided into two main phase, right? You can think of that phase. So we do the global route, mostly the planning, and then we use that planning for the detail route, right? So the objective was slightly different, right? The global route is try to plan everything out, see if look at the route ability, right? Whether it's is that possible to route the design cleanly, right? And we look at the congestion, so we can predict whether the route the route going to complete cleanly or not. And then detail route, when we actually use that planning or global route and then convert into tracks and I've laid out a piece of wire and consider all of those, two main things, right? One is the DSC or the geometry aspect requirement. Make sure, spacing all of the DSC is met, right? And then the second one are the electrical, right? So whether the route is efficient, um, SI is good, timing is good, right? So we cover all of that um, because reality is it's just so many things that the tool have to look at, right? So it's a trade-off. So usually the tool go through, you know, do a certain iteration, and then it has to finish, right? And for the easy design, very much after detail route, you don't really have to do the post route optimization because it's all the requirements are met, right? You have a no DSC, your timing's met, so very much that's the ultimate goal, right? Everything connected, um, no DSC, no open. That means your LVS is good. You met timing, right? but the reality is that that's not the case, right? So if reality is that when you run through the detailed route, you're gonna always come back with some issue, right? There's gonna be a number of DSCs. There's gonna be some antenna error. There's gonna be some issue that you have to look at, right? So that's where the post route optimization tasks come in, right? So I break this down into like two category. You can say it's the first one is kind of like obvious that things that have not been fixed, right? So you still have errors, you still have violation, right? So after detail route, we still have timing violation. So timing is not met, right? We do have some short or open, right? So the LVS is not good. We do have some DSC, right? Um, and we have, you can call it timing DSC, right? So the max trend, max capacitance, and max fan out is not met. So and then you may have some SI, right? Signal integrity issue as well. So those I lump into the things that you need to fix, right? And then on top of that, we still want to improve on the PPA, right? How to make the design better and more reliable, right? So those are, is it possible to regain some of the uh, area, right? Reduce the cell count, um, reduce the wire length, right? To improve the power area. And then is there antenna violation, right? We have to fix, right? To make the chip more reliable, right? When they produce a chip, more likely it's going to come back in working condition, and then add additional via, right? Wherever that we can. So those are the two buckets, right? Um, see here. So and one way to look at the routing stage is right. So if you say, well, I expect the detail route to complete with whatever the result is, what else, post route can do more, right? So the difference is that the, the trade-off between runtime and the quality of result, right? So the tool gonna try on a preset objective, it try to do within that detail route, and then if it's gonna run, and then at some point it has to stop, right? So essentially it has to give, it's look at the cost function, right? Time versus the quality result. So as I said, on a easy design, it's gonna finish with very much the result that you want. Everything clean, timing, power, all those qualities met. So there's no, ultimately there's no need for the post route optimization, right? But on a challenge design, you can have violation, and the tool can't iterating forever. So it has to stop. It's gonna give some trial, some iteration, it run, and then it's gonna stop. The reason for that is for the user, for the designer to have a chance to actually look at the violation, the error, and figure out why didn't the tool fix all of these, right? So because the tool just, without knowing everything that go into the routing, maybe the setup is wrong, right? The tool is not that smart to understand all of those things. So it has to stop at some point. That's where I think our experience come in and look at the result, right? Look at, why we still have DRC, why still have, open and short, right? So the tool gonna stop and the design gonna come in, and based on our experience, we're gonna look at it and say, oh, we over constrain, right? We add too many routing blockages. Essentially, we restrict certain routing resource to a certain area of the chip, right? It's just impossible for the tool to route cleanly, right? So the tool can't it's gonna try, but it couldn't figure out how to do it more, right? So those are the things that that's why the tool had to stop. And then the designer come in, look at the result and figure out what happened, right? Or things that we didn't set up correctly. So usually the tool, the way the tool operate is gonna come in and run as a preset of iteration, right? And then after that number of iteration is gonna stop, right? Because it think if I'm gonna spend more time, more likely I'm not gonna be able to fix it for you. So it's gonna stop, right? So think of that, right? When a tool try so hard and it's end up with violation, that means the designer, as a user, have come in and look at and try to figure out what's going on, right? So here I'm gonna just give you say so it's different tool from tool, but the general idea is the same, right? So if you look at the routing, this is one of the strategies the tool use about routing all these different steps, right? So number one, you think of is the global route. We come in, do the G cell, right? Blending all those steps that we talk about during global route. And we say, well, let's do the detail, do a quick routing, just connect everything, right? That's step two, right? To do the detailed route here. And after the detailed route, try to go in, look at the violation, and do what they call a rip and reroute. Or Innovus like to use the different term as search and repair. Essentially, it look for violation and I try to repair it, right? So if you think of the router, when they lay down the net, right? They lay it down first. Try to do it cleanly, but you're gonna have violation, right? So it's like, wow, let's connect, let's do the connectivity first, right? And try the best it can. And then it come back, look at the remaining violation and rip them out, right? And try to fix those wire, try to reroute them, right? So cleanly, right? So that's why they call rip and reroute, or Innovus like to call it search and repair, right? Same thing, right? So, and then it's going to try to do that over and over, right? Because more likely you're not going to be able to do it in a few iteration. the design is so challenged, right? So if it was easy, probably it was able to route it first time around, right? So, and it's so many possibility. So the tool you have to give the tool enough chance to try different things, right? So that's why the iteration come in. You have to try it, give the tool more chance, and then the key here is what they call Swiss box, right? So you think of like if you search for there's a violation, and then say, well, that's a net, right? A violation on a net. So that's net. It's very long, right? It's going through, you know, a certain area, expanding across multiple G cell. So you want to say, oh, I'm going to rip this net out. So what part of the net you want to rip out, right? Just a tiny bit of the net around the violation, or you want to rip the whole net out, right? So that's where the Swiss box come in, right? So the tool initially tried to say, well, I'm gonna limit the scope of the ripping out the net locally, very small, right? Let's say 1 G cell, and then try to fix it, right? Because you don't want to disturb. The key is you don't want to disturb the route, right? You want to just fix the DRC without disturbing everything else, right? So you start with a small box, you rip it out, you try it, and then say, if you can fix it, you almost done, right? You're done with that one violation, and then you move on to the next one. But what if you couldn't fix it? And I said, wow, maybe this box is too small. The Swiss box is too small. I have to increase the size, right? So the runtime gonna increase, right? Think about the 2 dimension, right? You have like, one, you know, 1 G cell. Now you have, 1 by 1. Now you increase in like 2 by 2. That's 4 times the area, right? So the runtime of the later iteration gonna, get higher and higher, but the possibility of, you know, uh, rerouting successfully is higher as well, right? Because we have a lot more possibility that you can try for the net. So that's the key, right? So it start with the global route, do the initial detail route, try to rip it out and fix it, and essentially do the step 2 and step 3 over again, right? With the difference is that every time the later iteration, the Swiss box gonna increase, right? So give the tool more chance to fix that net. So I think in the lab, I try to yeah, let's see, tricky to show it, but yeah, hopefully it come up with something can this much. So the rip and reroute, and then in the log file you can see it actually. Okay, so the next thing, let's see here. Let's see this one. So we look at that's the post route optimization. So the next 2 important things that so like a new concept, which is very important during this post route is the antenna violation, right? So one of the things that always very much always come up is the beside the DSC and LVS is the antenna violation. So first we need to understand why kind of like review. I think field touch on this on his introduction, but we kind of like go back and review why do we have uh, why do we care about the antenna violation, right? So the way to look at this is you look at how the IC is manufactured, right? So essentially it's just a series of layers, right, of material get put down one after another. That's why when you look at the tech file, it say how many layer, right? What technology, how many layer is it? So, and the way you think of it is that you build a substrate and you keep, add, you mass it. Uh, you deposit the thin film of whatever material, right? Whether that's like M1, M2, or thick metal, thin layer. Um, it's just a series of layer, right? So, and then it's had to etch it out, right? Essentially, you want to every single layer has come with a mask, right? So essentially, you have to create that mask somehow. Uh, so the process to create that mask is etching, right? So as you can see here, right, they use I assume the orange one is your substrate or the material that you want to deposit, right? And then here's your mask, right? And they use plasma to essentially etch it, right? So the result of this is you create the shape of the layer that you want. And the problem with plasma is during this process is create a lot of electron, right? The ion. That's the reason we care about the antenna violation later, is that during this etching process using plasma, there's a lot of ion, created as a byproduct of this. And if you watch the video that I share, they explain a little bit more detail on the process of how the layers get put down and etching and then removing the mask, and then just the process get repeated over and over again. So now the summary here is that because of the process we use to put down these layer, that's ion, right? And then because of that, the ion get a charge, right? So when we do layer after layer, and when we do the metal, right? So when we build this up, some wire, especially the long wire, gonna have charge, keep building up on them. So as you can see here, so so this is the gate. And then say we build the VR1, 2. So let's say this is M2, right? So we have very long piece of M2. And then during that process of plasma, etching, a lot of charge get, over here. And because of the wire connect to the gate, and the gate has like very tiny, very thin piece of metal oxide. Right here you can see as the piece of gray right here. And if the charge is large enough, it can damage it. So so that's very much the antenna violation, is that there's 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 a rule to look at. You look at the gate area, and then you look at the antenna area or the collecting area, right? And say, wow, that ratio has to be less than a certain number, right? So think of it as like, okay, I'm going to collecting all these charge. So the longer the wire, more area, right? That means potentially I'm going to get more charge. So that the likelihood of damaging the oxide here is higher, right? So if you look at the library, you see this number, right? So that's the ratio for this gate. So every gate gonna have that ratio, and that's what the tool check for. Is that ratio less than a certain number? Um, yeah, think of it as, yeah, and I think in this case, antenna is the name is very totally obvious, right? So the piece of wire collecting charge, right? So, and if that piece of wire is very long, the area is high, right? Very large area, then it's gonna collect a lot of charge. And then when it's connected to a gate, potentially it can damage it, right? So, okay, so that's the antenna violation. So how are we gonna go fixing it, right? So now understanding the reason, we're gonna try to fix it, right? So that's two things, right? You two things that you have to understand the process. So we're gonna, if you look at this piece of wire, connect from the source here to the gate. We do it like process, right? Do it layer by layer. They not connected at its, all at once, right? So we do the M1 here, and then we do M2, and then we do M3, right? So if you look closely, the the difference we try to do here is we break the long wire, right? So this method they call a jumper, essentially preventing the tool on the long piece of wire to connect to the gate, right? So if I go back here, uh, so when I put down the piece of M2 and it's collecting a lot of charge, it's connect directly to the gate, right? So the collecting area is very large, right? So potentially damage the gate. So, and then in this method called jumper, so when I'm built up to M2, so you think of this way, I don't have M3 yet. So the M2 that actually connect to the gate is only this via stack, right? I just have the via stack right here. So I'm fine because the collecting area for the charge is tiny, right? So the piece of long wire here, it doesn't connect to the gate. It's connected to the diffusion, the source, which is fine, right? So the charge can go that way. That's fine. It's not gonna damage my gate, right? So the key here is the gate right here, right? That's what we care about is this thin metal oxide, right? So So the difference is that you can think of this way, we cut the wire, right? Instead of do the M2 straight, we actually split it and we go to a higher layer, right? So we say, well, just don't do a straight wire. I'm gonna cut it. I go up one layer, right? So by the time you do the M2, it's the wire is not connected yet, right? So and then whatever charge that deposit here, this has been relieved, right, to the substrate. So by the time you do a M3, it's fine, right? So when you put an M3 here, you don't have that kind of like accumulated charge anymore, and you fine. So here to summary, I have here, right? You essentially create or add the jumper wire near the gate, right? The key is you have to do it. Two things: you have to create a split in the net, move them higher, and it has to be near the gate, right? You don't want to do over here, because if you do over here, you still have a long wire connect to the gate. Then it's kind of like defeating the purpose of, having a small area, collecting area, right? So this is a very effective way to fix antenna, right? Because it's pretty simple. When there's a routing resource, you just split, the tool gonna just split the net, and they go one layer higher, right? That's it, right? So, but it's not always possible, right? Think about instead of this M2, I'm like at M6 already, right? So I'm like at the top layer already. Then you can't jump anymore, right? So, or you routing is the piece of metal is M2, but then you have like M3, M4, M5 as a routing blockers. So even though M2 is not the highest layer, but realistically it is a highest layer for that area. Then you very much stuck. You can't jump anymore, right? So that's called it. This sometimes you can't fix it with just the jumper, right? So we have to have a different method for doing that. So any questions so far?
Nothing in the chat so far.
Okay. So I assume everybody follow and understand everything. Uh, so again, the key is you jump the layer, right? So you split it, the long wire, you move to the next, and make sure that jumper is next to the gate, right? That's the key. Okay, so I'm gonna give you one more example here. So let's say we have a net. It's just not one source and and one destination. Let's say we have multiple fan out, right? So if you look at this one, say number one here, it's a two-way of doing it, right? So let's say I have the violation on these 1, 2, and 3 because it's connect to the gate. So I can put in like, oh, I'm going to jump right here, 1, 2, 3, right? Or say, well, why I have to do 1, 2, 3? I can just put a jumper here and potentially fix 1, 2, 3, right? So can you tell me which one is you prefer and which one is not? right? One is essentially you have a high fan out net with a multiple antenna violation, right? You can do essentially on the left here, you can do locally for every single violation you put in the jumper, right? So you can have multiple wire chains. And on the right here, say, well, I'm going to look at the common portion of the net, and I'm going to do one jump, right? So think about it, right? So what is the difference, and what is preferred? Which solution is preferred? And which one is more realistic? Yeah, if you're not, yeah, you can put it in the chat if you want.
So one student has said that they think left is the better way. No one
So
else was
put
brave enough to
in,
answer.
so let's see. I think the left is better way. So essentially he's saying put in multiple jumper, right? Okay.
And explain why it's better.
And go Thái and Hào, why do you think it's better? How? Yeah, think of this way, right? If we go back here, just review one more time. Yeah, the key is you want the jumper to be next to or near the gate, right? So to reduce that collecting area, right? So you want to be near. So the difference, at least, the between the left and the right here is the left, you put in a jumper individually for all these gates. That means you have it right there, right next to it. So on the right, instead of do it right next to the gate, you look for the common portion of the net and you do it. So you do have a little bit of extra wire here, right? So for each of these 1, 2, 3. Right. So his answer is that it's as I mentioned, right? So it's good to be next to the gate, right? So the difference is that, right? So what if this the solution on the right, if you put it in and then you still meet you still able to fix the antenna violation, then if that's the case, then the solution on the right is better, right? Because you very much reserve the net better than the solution on the left, right? On the left, you very much have to change three segment of wire, right? So it changed, it affect the topology of the net more, right? It's disturbed the net, the routing more than the solution on the right, right? So, but the solution on the right is not always possible, right? Because more likely, if the common net is, so this jumper is, it's a little bit too far. That means whatever the piece of net here is still, large enough. Then you're not going to be able to fix it, right? So if that's the case, then you have to go back to the solution on the left, right? So solution on the left more likely will fix the antenna violation, but you're going to use 3, right? You're going to disturb the net more. The solution on the right is better if you can actually fix the violation, right? So that's a trade-off, right? So I think the tool is good enough to figure all these things out, right? So it's gonna try and pick out the best location for the jumper to add, right? So just enough to fix the antenna violation, but it doesn't have to do the, every single one, right? So it's a look for the common point and they put it in for you. So that's so we cover the methods for fixing antenna, right? So again, the idea is to reduce the collecting charge area, right? To make it tiny, right? So if we end up with a solution, we end up with a piece of wire that doesn't give us the option to jump, right? Add in the jumper, and what else we can do. So the second method is that, well, instead of change the wire, we're gonna add in a diode, right? So the reason we try to do the jumper is because we don't want any charge to damage the gate, right? Because the charge go through the gate, it's gonna potentially break it. So with the diode, say, well, if there's a charge, then it's we give it an option to go through the diode, right? So that's the reason behind the second method here, is that we connect a diode next to the gate, right? So we give it the option for the charge to connect to the substrate, right? So as you can see here, right? So if the charge here, then we have the diode here. Then the charge can go through, the diode, go to the substrate and protect the gate is protected. So the disadvantage of the second method, usually that's why we don't want to do this second methods, is that because you add extra gate, right? So first of all, if the area is very congested, or the density is very high, it's just not an option, right? You don't have an area to add a diode right next to the gate, right? So and then if you still have the area, adding more gate does increase area, right? So usually you're looking at 2 options, the jumper and the diode. Usually you want to try the jumper first, right? Try to see how much you can fix, call it the first option. And then the second option is just try to fix what's left over, right? So, and then if you try to do method 1 and method 2, and then the tool couldn't do it for you, then you have to look at and say, well, you may have to do something, give the tool something that they can work on, right? So, but understanding the reason why you have an antenna violation, right, is that because the way that the layer or the chip is manufactured, and understanding that, then when you see the violation, you can come up with the right solution for it. Okay, so I think we cover, let's see here.
So the question is, can you go back to the other page?
Okay.
The question is that which location is better for the diode? Is that to the left of the gate or to the right of the gate?
Yeah, I think this is just an illustration here, but yeah, ultimately certainly you don't want to create extra piece of wire here, right? So ultimately you want to connect to the existing piece of wire. So the diode have to be here, right? But this, I think for the illustration purpose, they want to write they want to run the diode outside of the, let's say that's a existing gate, right? So I think it's more like over here, right? This is what you want, right? So you want to diode connect to a net right here. You don't want to certainly create a new additional piece of wire just to connect to the diode, right? You want a diode to connect to the existing piece of wire next to the gate.
Yeah, this is advanced topic, but in case you do an SOC and you don't have visibility to, say, an analog block, for example, this is an analog block, and you have an input, and you don't have visibility on the routing inside here. So one way in practice we always do is that to make sure we don't, because this is a black box, so to 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 be correct by design, you can insert a diode here, right? At at every input of the analog blocks. So you don't have to worry about, you know, all these wires, because when it comes here, the diode will collect the charge. In case you have black box. So just some note.
Right. Right. So those are usually come in with the understanding of the design, right? So and usually, you know, the first few iterations through the design, you see, you know, this interface with the more likely that you have like many long wire connecting to that, you know, IP or analog macro, as Phil said. Then yeah, it's a trade-off, right? Just you don't want to say, okay, I'm gonna run through the design and see how many antenna violation I'm gonna come up, and then try to fix it. So every time you run it, you say, wow, it's only come back with, you know, it's quite a few number, and it's very, you know, every run is slightly different, right? So because you look at the ratio again, right? Not every time every single input or pin will have a violation, but majority of them have. So the trade-off is yeah, just go ahead, as Phil said, just go ahead, add all these diode, right? So and then you come to the end, you don't have to worry about them, right? So every time you try to touch the net, potentially something gonna pop up, right? So you fix antenna, and then your timing was clean before, now it's no longer clean, right? Because whenever you touch the net, the RC change, right? So and then right, so the you essentially you pay the cost upfront. You say, well, I'm gonna just, you know, pay my cost now by inserting a bunch of diode, and then I don't have to worry about them later. So thank you, Phil.
Sure. Yeah, just keep in mind that is only for black boxes that you have no choice. But Yeah. But usually you don't insert diodes everywhere. Yeah, because of the cost. Right? But for analog blocks, inserting a diode in the input of a digital gate is really just, it's not a big deal. Right? Yeah.
Okay, so let's go back here. So we went to the post route optimization, the via optimization. I mean the antenna, and then the next one is the via optimization. So as I mentioned before, you know, we look at the post route optimization. Here, let's go back to the slide again. So you can split into like two, right? It's more as like the error and violation, and the second box here is reliability and PPA, right? So antenna violation and redundant via fall into that. So let's see what are the redundant via, right? So the idea is that up to this point, right, our concern was more like every net needs to be connected, right? So that means a single via is good enough, right? So between the layer, right? So that's all we need, a single via, right? So why you need an extra one, right? So the reason is, right, manufacturing, right? So and it's listed some of the reason here. Could be random effect, you know, misalignment. So having multiple via gonna increase your chance of that net actually be connected, right? So so those are the reason for having redundant via. So now we look at this one. Let's see, look at the picture here. Okay, so a little bit color coded here. So this is the black one. The black via was the original, right? And then in this case, 3 of the via we was able to add in a second via, right, or the redundant via next to it. So instead of having 1 via, we have 2, right? So we have 2 via for here. That's connection, and we have 2 here. So in the example that we have here, we have 3 via. We was able to convert 3 single via to 3 double via, right? That's the conversion of 100%. That's outstanding. On the right, however, so because of the existing wire, right, and the topology, not every single via can be converted to double via, right? So let's say, so we look at here, so the color code here, they say via candidate, okay. So if you look at the via one, there's only one little location here that we can add redundant via, right? So for the via 2, there's no candidate, right? So that's why a via 2, the term used for is that it's a dead via, right? So it's essentially there's no location next to it that we can add another additional via, right? So that's it. We have to leave it with a single via. We can't add more. And then V3, we have 3 different, let's see, 1, 2, 3, yeah, 3 different option, right? So one, we have one option. Two, we have no option. And three, we have three different options, right? So and let's see here. So this is where we did talking about what I call it's more like routing strategy, right? So some people actually say, well, let's do the routing first and then do the optimization, right? The via optimization. Or when the tool does the routing, take into account, it try to put in the, or planning to put in the redundant via, right? Because when everything routed and then you come in, you very much just look for opportunity to swap out, right? So, but then when you do it, dynamically, the tool can plan for it, right? So yeah, I mean, every via, I want to at least an option to convert into a redundant via, right? So the example I'm showing here is, you look at the picture A here, right? So let's say we already have this net routed, and then we in the process of routing this, say the second net, right? So from the source here to the target, right? So we can go with option B. We just go straight up from the source and then go left to the target. That's perfectly fine connection, right? It's everything is perfect except for by committing to this route from S to T, we converting, essentially we blocking this via, the existing via of the previous net, right? So we leave this net or via with no option, right? It's like we're making that existing via a dead via, right? So because we're blocking it right here, so it's nothing this via can. There's no neighbor as can be added, right? So that's option B. So if the tool have the redundant via capability, then it's kind of like think ahead. It's like, oh, I have multiple option, right? So I'd rather do this option, the C option here. So I'm gonna ship the track, one track over, and I route it this way instead of go straight up, right? I go left first, go up, and then go left again. So that gives the existing via a possibility of adding a redundant via, right? So that's the difference between B and C, is that, yeah, C, when the via avoidant or redundant is, the route is aware, then it's planned for it, right? So instead of the B, it's just route without thinking about oh, the via need to have the redundant via later, right? So okay, any question? So we exactly at 1 hour. So I think if you have a question, you can hold up or just, I think time to take a break, like 5-minute break. And then if you have a question, you can type in the chat, and then we can.
Yeah, so
Rest.
can I put a poll on about the final project? I want to have a few moments to talk about final projects in case there are questions. But if I can start a poll and students can fill in the polls during the break, that would be good.
Okay. So you have
Me-
something ready you can post still?
Yeah, yeah.
Okay.
I'm first time I do it, so it might be something. But I work now. I can save and post.
Okay. So let's try. I do see it. Okay.
Okay, I just launched it. Okay, it looks like it works. So we can go to 5 minute break, and if the student can fill out the poll during that time, it's good. Thank you.
All right. Thank you. Okay, I think time's up. So Phil, do we need more time for the
Yeah,
result to
looks
come in?
like it's only 44 hours 72. I don't know how many students we have, so I am under the impression that it might be 60. The goal is please fill in. I want to see every student's answering it. But while we're waiting for it, I can um, uh, does anyone have any question that they can start asking here? It can be in Vietnamese as well, if you're more comfortable with asking question. Yeah, please do, Minh. Yeah, just unmute and talk. English or Vietnamese is all right. And others, if you haven't filled the poll, please do so quickly. Minh hỏi đi, Minh, Nguyễn Lê Minh.
In step 3 in the final text, I want to select the core to add the powering and something like that. But like it's I don't know how to select it. Like for the macro select is easy, but I don't know how to get the name of the core to get selected. Like I create it, but I cannot select it, so I cannot add the powering. How do I select it? I know it's kind of the question.
Yeah, okay. We'll note that, and we'll during the lab session, somebody will show you how.
So just to be clear, he asking how to select the macro, is that right?
Yeah, because he doesn't know what the name of the macro and all, right? So if you build a ring around the macro, how do you do it? So we can show him interactively. He can pick select the
Oh,
macro
he want to see
and
the core. He say, I mean the core.
the macro, right? So it says memories, and what is the full name of the memory? So he can say select it and build a core around it. You know what I'm saying? So if you build the ring, right? You build the power ring.
Oh, I see.
Yeah. So you need to have a full name of the macro and say build the ring around this macro.
I see.
Or he said mean the core. Okay, we will review that. Yes, we'll review that. Okay. We'll pick a time in appropriately, perhaps next week or near the end of this lecture to show you. Okay. Yeah. Còn ai có câu hỏi gì nữa không? Anybody has any other question? We still have only 47 hours of, but I guess we can end the poll now. Anyone else have a question?
I have a question.
Okay.
I want to ask is that we can change any content of the file in the input directory.
You can change as long as you don't change the requirements. For example, you cannot change the order of the IOs, or you cannot change the constraints unless when you try to improve the speed, then you can create another directory to run your new run. Then you can change the SDC, the constraints.
Yeah, like I just want to change the path of the files.
Or the path to the file.
Yeah.
Yeah, you can change that. You can put it anywhere you want. Did that answer your question?
Yes, thank you.
Okay.
So he want to change. So okay, just try to understand the reason. So it seemed like he tried to run multiple experiments. That's why you have multiple copy of certain file, right? And then you want to point to that different file for multiple run. Is that right?
No, I just have the place where I run Innoverse in the different place. So there are some parts in the MMMC file that is not match my place. So I have to change it. So in order to import the design.
Yeah, so you would copy all the inputs to your run directory, and then you would change the path to those inputs, you know, separately. So your path, the path to your input is different than the path to other people's inputs. Right?
Oh, so the setup is not relative in field, it's absolute. That's why they have to do that. If we set it up in a way that is kind of like independent or relative, then they don't have to do that, right? So wherever they copy to, it should work.
Yeah, the instruction doesn't have any scripts, right? The instruction is that copy the documentation, the input directory, and the instructions. That's it. And then they
Oh.
can create a script anywhere they want, but don't point to the inputs. You copy a whole thing to your local directory and you do whatever. Yeah, they don't have any script.
Yeah, they know
Okay.
the whole thing is a package or relative path. So if they move it, they have to update the path accordingly. It's all relative path. So
Yeah,
it's
yeah.
full
So
package.
the instruction is relative path, right? But the script, there's no script. So they build the script from scratch, so they can put whatever path they want.
I see.
Okay, Võ Thế Dũng asked, can we receive a checklist in each phase to check after we finish? That's very good question. So we can do that.
And Phil, the checklist should be if you after each of those lessons, right? So after placement, what are the things we care about, right?
Yeah,
We talk about sanity check. Those are your checklists. We shouldn't
right.
have to create another one. Those are your checklists. After placement, after full planning, we have those checklists, the sanity checks. What are the care about, right?
Yeah,
So after
yeah.
CA,
I think we should consolidate them, and I don't think we have checklists for every step. So it's
no, yeah,
something good to review, right?
yeah. But those, if you open up the slides, right? You should see those in at least the slides that I taught in terms of placement and CTS.
Yeah,
You should be
yeah.
able to see those.
So you're very good at that. I don't know if I was that good. So we'll, and I don't know if Tien has anything, or in the future or not. But yeah, we'll consolidate and share as a quick review. Right. So we'll do that next week. Okay, Dũng. Any other question? So let me share the results. Where did I just hit the share? I don't know where it could go.
I do see it.
Is that what I'm seeing here? Like I'm scrolling it.
No,
So
I see.
oh.
It just popped up on my screen.
Okay, so maybe it doesn't pop up in mine. But so first question, did you start working on the final project on the cloud? So 83%, 39 out of 47 say yes, they did. And so 17% did not. So the message is that please start as soon as possible. The reason for that is as you go through each step, even though you haven't finished the lectures yet, but if you go through it and you run into difficulties or you have questions, you can ask along the way, like today and then next week. So we have time to have mini reviews for things that you need help with. We're not going to be able to review everything due to the limitation of the time we have. We only have the final week, like only one session, because we plan for 2 sessions in the final week for reviews and work and office hours. but because of the surprise April 30th holiday, so we lost one lesson. So we only have one lesson at the end. If you wait until the end for reviews, or question answer, you will not have enough time to finish. So by trying it now, you have a chance to say, hey, review this for me, review that for you. So targeted reviews, because that's the only time we have. So we try to insert and steal time from Tien's lectures to answer the question along the way. Hopefully you be able to ask questions early on. Okay, so please work with your TA and start playing with the project. 2, did you run into any difficulties? So 70% say yes and 30% say no. So it's a very big one. So if you run into any difficulty, your first line of defense will be your TA. But if they don't solve it, then they bring it to the class, or we have weekly meetings with TA, the Thursday morning, the day before the class. So we can address there, but if it is on Tuesday, then they can bring to the class and discuss things that they could not solve. Okay, so because of the timing, please run through the difficulties with them first, and then we'll address them anything on next week on Tuesday. Right? Is it, sorry for the grammar, is it clear to you how you can sign up for more virtual machine times for the project? And 89% say yes, and 11% say no. So I'm going to say it again. So the virtual machines are available 24/7, 7 days a week for you, but it will not be open all the time, but it's on request, meaning that if you plan it doesn't matter what day, there's no limit on what day. Okay, if you think tomorrow at 7 o'clock a.m. or p.m. you're available, then tell your TA you want to sign up for your certain time slot. And if you sign up, you better use it, because FPT pays for it. And if we sign up and don't use it, they will be it's going to be wasteful. So that's why we have a registration or sign up system. So you only sign up for the time slot that you can make it. So that could be individuals, but your TA will consolidate all the requests and submit a requested form. So please work with your TA, and again, the virtual machines will be available anytime you need between now and final project, anytime, any day. Just put in the specific time slots, and then your TA will work out. Each TA, lead TA will work out a sign up. Okay. Do you have a list of reviews that you think you need in order to do the project well? So 57% say yes, and 28% no, and 15% don't know yet. So it's about 70% need the review. So please let your TA know ahead of time, and then each class day will please TA send the questions first. Either I think probably the best would be on the stream of the Google project, Google Classroom. So say, here are the questions that my team is having. And then based on the list of questions, we'll plan how to answer them in each class, right? How to prepare the reviews for each class. So the sooner you let us know, the better. But if it's last minute, we will not be able to prepare the reviews for you. So let's do it day by day. Each week we'll have 2 reviews based on the specific question you have. Again, don't say review everything, because we won't be able to do that. Okay. So that's all I have. Any additional comments? All right, all yours, Tian.
Okay. So actually, that's all I have for today.
Yeah.
So
Hey,
do you have?
let's
Yeah.
go back to, I can answer the students on the questions on how to select RAM and memories and stuff like that.
Okay.
So
Do you have something to share?
yeah, I can share.
Yeah.
Let me know when you can see my screen.
I can see it.
Yes.
Okay, there's a couple of ways there in this design. This is your final project. Okay, there are 4 macros. Okay, so there's 2 ways of doing it. You can do in the GUI. You can go to the design browser, which is this guy here. Okay, and you can grab it by instant name. Here's this instant. Just do star RAM. So you will see a lot of RAM coming up, right? This is an instant. This is one RAM. This is the other one. The rest is just it's got the RAM name, but those are the mux and stuff like that. So this is one way of doing it. Okay. The other way is you can go into the on command line. You do get db instance, and you can do star RAM. But this is going to give you a whole bunch of RAMs, right? So a better way of doing this is to get the base cell's name called RAM. So you can do -f dot base cell basically is the cell name like equal to star RAM or something like that, RAM. So it will give you come back with just the RAM name. So as you can see here, the 1 instant and 2 instant, which is the same 2 instance that you see here, right? Likewise, you can do the same thing here with the ROM. You get the instant name of the ROM here. See, the instant name would be from here, right? You can do here also. You can do ROM, and this happens to be only one ROM. There's no mux along with it, okay? And there also we have another macro called it's a PLL macro. So here's the PLL instance, right? You can do up here also. Just do PLL and it should come back. Okay, so that answer you guys questions on the file instance. You can do the same thing for any particular instance name that you want. You can use the getDB command instance. Okay, if you don't know how to do getDB instance, you can do a help star instance, and it'll come back with a whole bunch of where you can grab it. Okay.
And the PLL instance, you can see the whole path, and in your instruction, actually, it has that whole path, right? So you can pretty much don't need this, but that's how you select, right? So let me share the screen. Are you done with that sharing? Maybe we can go back to what you share. Maybe if Tian doesn't have anything else, we can go over a little bit on the project, right? So show them
because
a
I
little bit.
think the original question was he thinking that he need to determine the core area before he can add
right.
the ring around it, right? So I'm not sure what in the instruction that somehow suggesting he need to do that.
Yeah, I think the Enfield, where did you? I can pull up the lab instructions. Is it?
I can share the screen. I have it here.
Okay.
Let me see. Screen 2. Sorry. I should not. Did I? Stop share first and find the. I thought I have the file. Okay, let me bring the file over.
Yes, specifically he say in step 3.
Oh, how to select it? Yeah, I show you. You can use several ways to select it also.
Actually, I should do the project myself as well.
Yeah, we need you to add to the questions and all.
Yeah,
Tian,
right,
so
yes.
I'll show you. So are you talking about add a ring around the core? This one, right? I forgot
Yes, sir.
who.
That's about that
Right.
thing.
Right. So if you offset from the core boundary and all, I think there's a command, and via that command you say is a core ring. I don't think you need to select the core, but I might be wrong. Yeah, but I'll provide you with the. I don't want to show the answer here, but the right command by specifying this is a core ring instead of the ring around a macro, then the tool will find the core boundary for you. That's what I think, but I can verify next week.
No, that's true, and Phil. That's I can verify
Yeah.
because I wrote the script. It's called the command is called. I mean, it's rings.
Yeah.
So you do a Y column rings. Okay, there's command called
Yeah.
add rings. Okay, there's there's two. I can give you a hint. Add rings and add stripes. Those two commands, you can do everything with the PowerShell.
Yeah, right. And do a man page on. So the ring, there are different types of rings, right? So you do a man page, and you will find out what option you to use to say it's a core ring, right?
Yes. So
Yeah, I think we have a lab on that.
Yeah. So
Yeah.
do review and go through the lab. You see the answer. So we don't want to provide the answers for you. Okay.
yeah. So yeah, just do a help on add stripes and add rings, and it will man page on that. You
Yeah.
figure it out based on the instruction. You figure out how to do it. But
Right. So so the answer is that he doesn't need to select it. He doesn't need to know the core size, right? So
no,
Right.
if you need to select if you need to create a ring around a macro, you need to select the macro and do add the ring.
Yeah, and you do need that over here. You see this PLL is in macro.
Yeah, that
But
doesn't.
I already provide the pathway. At first, I thought you asked about this path, but already tell you. But this have the full path for the instance, okay? And then you also use the right command to add the core ring. The ring around the macro. Okay. And maybe Tian, do you have anything to cover? If not, then Bud can just navigate around the project, maybe show people something, or open up for questions right now.
yeah, I think open up for question anything.
Yeah, right.
know.
Right. So, but do you want to bring a share again, and or
Let's open up the floor for questions to see if there's particular area that the student is concerned about. We can answer those first.
Yeah. So maybe we can go over. So before I just go over, right, and then you can ask question along the way, right? So here, so the assignment, right? So you just need to run with the following: no DRC errors, no design rule violation errors. So design rule violations are max transition, max fan out, max transition time, max fan out, and max
Max cap, yeah.
Max cap. All right. And then there are no timing violations, right? So if there are timing violations, you have to run through fixing to first you fix our no DRC, no DRV, and no timing violations. So you might need to iterate, right? and to get everything. And then after everything is done, you pay attention to total cell area. Total cell areas meaning just the standard cell areas, because the macro areas are fixed. So why this is important? So if you meet timing and you have everything clean, then the total cell area will tell how efficient your design is. Meaning you can meet timing, but your cell areas are bigger than others, then that means that you consuming more power. So you waste more power. Then the other design is better, same speed but less power. And then if you meet the speed, if you have less cell areas, you have less power consumption, or you might not, because the power consumption has also the dynamic part of it. So the total cell area can affect your static power, but dynamic power depends on different things, like slew rate, like the caps of heavily switched buses versus not. So the total power consumption is another measuring stick. So if everything is clean and you have small cell areas, you have more bonus, or you have less total power consumption, you have more bonus, right? So those are the criteria. So now, so like I mentioned, you will copy over, you don't refer to the project at all. So you have a work area, you have your homework area, you create something. So say final project or whatever. So I suggest this project, just follow this format so we know where to look for your final result. So then you cd to this and you copy -R to copy everything under DTMF chip. So basically just the inputs and documentation, no script or whatever. The scripts are the things that you're going to create. So design information you already went through. So the top level design name is the TMF chip, right? And there's a net list, and note the AK. I don't know what AK is for. But there are multiple in Verilog. You take this DTMF chip AK.V as your input. So this is gate level that is generated from a synthesis step. And then timing constraint, you have an MMMC command of constraint files. If you look into MMMC, you have you should know what are components on MMMC. Review your information, and you will see there are calling of the library, timing models that lib files, and you have the extraction corners, right? RC corners in there, and you have the timing constraint SDC, and you have analysis views that you have for active analysis in setup and hold. And then you have the physical views. In this case, if you in the lab, you have a technology left and you have all the cell left. Technology left are the place around technology files where you have all the rules defined and all is used by the Innovus tool. And the abstract left are the abstracts of all the cells that you use in your design, including standard cell libraries and also the macros and also the IOs, right? So all the left, in this case, to make it easy, everything is in one. So you look in there, you can see the rules, you can see the technology information, and you also see the physical abstract information of other cells. And then in the floor planning constraints, you will have one file called dtmf.io. If you recall, this is a file that controls the placement of the IO pads. So when you use this file and you import the design, you will build the floor plan this way. and you see all these things, or the path order, like what are specified in the IO. So the path, you can see there are corner cells as well. There are 1, 2, 3, 4 corner cells, and all these paths. So you notice there are space between paths, and all in reality you have to fill them with filler cells, but this is basic. We don't want to make it too complicated. So it's okay to have this thing here not being continuous, but in real life it needs to be continuous. But in any case, you will have this IO as a constraint on basically the order and which side certain IO is on, including VDD and VSS in here as well. Okay, see, and then for the placement part, so after you do the floor planning and all, you have a placement part where you have a scan chain definition file. It's called scan chain.def. It's not definition, but def is the design exchange format. But in this describes your scan chain. So this is used by your place and route tool for scan reordering and all. And then you have filler cell list. So these are the filler cells used in the standard cell area. And this is, if you place the cells and you have holes in between them, the holes have to be filled with the filler cells. Yeah, and these are just no caps for basic fundamental class. We don't insert filler cells with cap, but in reality you will have to deal with them. But for this you only need to have filler cells. And then if a CTS, you have certain constraints related to CTS. Specifically, you have a buffer list that used for clock trees, and you can see CLK buff different sizes. So X1, X12, XL is extra small. XL is really the smallest, I think. And then inverter, right? So you will be using both buffers and inverters for your clock trees. So these are the input. Sorry, it's not very clear on the format, but these are the project data that you have. So the step you will take is step 1, to import the design, right? So you will create the script, right? No script provided for you, but you can refer to the scripts in the labs and build your own script. And you can build your own script by reading the MMMC file, import the left files, and load the netlist. And keep in mind that the order of the commands is important here. So refer to your labs and see how is it done, and follow the same set of scripts, the order of the scripts, and create your own script to import all the data that you saw you copy over earlier, right? And then in that script, you will tell the tool that the power and ground nets are VDDs and VSS. So it's a quick review. In the net list coming from synthesis, these are logical. So there's no power and ground which are physical. Power and ground doesn't exist in the logical view. So you will need to tell the tool what are the nets. So these nets are the net names that you connect all the pins of the cells. The macro cells have power and ground pins. The standard cell have power and ground pins that you use a command to connect those pins to the net name VD and VSS. So, and then you run that command to connect. You say what are the net names, and then you run the command to connect all those power and ground pins to the nets. And then you read in the IO placement cell file. So in addition, you will need to tell you importing and you creating a floor plan, initial floor plan. So initial floor plan, you will say it will be based on a core area. So you say first the core will have a width of 842 micron and then the height of 842. You say there's a command, and you run. There are different ways of building a floor plan. In this case, will start with, hey, I want to generate a floor plan. Here, there's a command, but using the core, right? So in here you say core margin by IO. Do a man page on create floor plan. You see what this means, right? And then in that you will say you need to specify the site name. So site name is TSM3 site. Site is a unit tile. It's a unit cell of a standard cell. A single unit standard cell has a site name as defined in your place around tool. So you have to specify that. So it will create rows that will be based on the unit tile. So it's stem, or it's like this is a unit atom of the core. So you say, yeah, use this site, and then you say core size, right? So you say width and height. You put in the width and height, and margin is when you say, okay, from core to IO, what is a core to IO distance? You put in 100. So by having this command, after you execute it, you will see something like this. Okay, no macros yet. These horizontal are rows that you just created using this command. Okay, and then after you've done that, please save the database to a predetermined location. So if we need to, we can go and analyze your database by putting under, this is a relative path. Your run directory put under data DBS import DB. So you use a command to write the DB out. So you will look in the lab and see how that is done. And then all your script that you did before, save it in here in a file called import article. So we'll take a look at how you not only the result, but how your scripts are created as well. So these are predetermined locations to help us look at your result. And then same flow, right? After import, you do a placement, and you write the script as a common UI. So you've been using common UI. So you use the Tcl script to place all the macros, and when you place the macros, you need to add halos. You know how to do it. So and then you in order for you to place the macros, the location, the orientation, meaning rotate left, rotate right, or flip or whatever, you use a flight light to help you determine where each macro should be. Okay, so this is your differentiation. Different people will have different placement of the macros. So you do this and look at the labs, and then copy it and do it over here, and you can play with the placement of the macros. After you run through you try one time and you run through and you see timing, and you might want to change the macro placement if you think it's better for timing. So that's your iteration. But try something first and then see what happens. But do use for the initial placement, do use a flight lines and your understanding of a good floor planning. For example, put the macros to the edges is there, and then having a very nice square rectangular placement area is the fragmented. So you review all the good floor planning practices in order for you to place the macros in their optimal location. right? And again, we save the macro, the DB and the script in these predetermined name and places. And next, we'll create power grid. All these things you already learned, right? So create the power grid, you already touch on that. So in here, you say, what are the bottom and top? Meaning over here, you see metal top is what? Top and bottom is metal 5 and right and left is metal 6. You can see here, this is metal 5 and this is metal 6. So you tell the tool, build a core ring, right? And then you say top use metal 5 and right, left and right use metal 6, and the width of each of it is 8, and the spacing is between them is 1 micron. And offset from the core boundary is 1 micron for all sides, meaning that okay, is a zoom in here, but this is not assuming this is the core. So offset from the core boundary is 1 from the core boundary to the start of the ring. So that's what it means here. So if you zoom in here, that would be 1 micron between the core and the ring. And so you use you look at what the command is, and then look at the labs, and you know what to do there. And then you can find out that all the macros have the rings around them except one macro, that is a PLL clock instance. So this is the one that you need to build the ring around the macro. And you look at the lab and say what command to use to build a ring around the macro versus around a core. Okay, so specification is similar to the core. And then the straps. So after you create the core ring and the ring around the macros, you can create straps. Straps are these vertical straps, or sometimes you call stripes, right? Straps or stripes. And here are the directions. So metal 6 in oranges, right? So you say build the strap vertical, mean go up and down with a width of 8 microns, and the spacing between two wires is 1 micron, and the offset from the left core boundary is 100. And what is the spacing between? I think there's one missing here. It's spacing between straps should be 100 as well. I think I have to add to it. So apologies. So you the spacing between pound ground straps. So straps come in pair. So the vertically you see pair here, 1 VDD and 1 ground. So spacing between them is 1 micron, but the pitch, meaning from one group to the other, is 100. I think so. I will apologize for a mistake there. I will add to it. Say you need to there's an offset from the left where you first strap starts, and then there's spacing between the pairs. So I'll add to that. So by and then you need to specify the connections, mean metal 6 and bottom layer metal 1. What you're telling it is to build and then veer down where you have cross, where you intersect, then veer all the way down to metal 1. If you don't want it to veer down to all the way to metal 1, you say 4, then it will be connected to 4 only, and don't veer down to the lower layers. In this case, we want it to metal 1 because we want it to veer down to all the standard cell rails. And then you use the route special to really connect all the pins to VDD and VSS, and you say do everything from metal 1 to metal 6. So block pins block pins, meaning the macro has a VDD VSS pin, pad pins, pads have VDD and VSS, connect them, and pad ring, core pin, floating stripes. So all these stripes and everything. So use that command to start routing all the VDD and VSS together. And that means that all these pins connected to the straps and the rings, everything connected. Okay, we have 7 minutes. And then after you're done, you will see these kind of connection. You have vias connected to the VDD VSS ring of the macro, connect the straps connected to the metal one horizontal of the standard cells. So you see all these vias. That means you do it right. And then you save the database and script, and you run placement optimization. So in this time you already have everything, and you just run placement optimization and you do a timing report. And if it doesn't meet timing, you iterate, you do things to fix the timing. And the difference between this and the previous one is really you run a lot of atomic command called place opt. But these not atomic, but these are macro commands or super commands that does a lot. When you run this place off, it does a lot of iterations inside. But at the end, you will need to report timing. And you look at the timing report, whatever you save here better be clean or close to clean. Just your decision. If it sometimes it's not clean, but you can fix the timing later, yeah, then it's okay. And after that, you run CTS, similarly, just optimization and timing report and make sure they're clean. In this case, I think, yeah, at the end, so the CTS two-step, right? As you know, the first step you build the trees, and then the second step you will run optimization for timing. And here, I think we're missing the. I'll make a note. We want to have a clock reports as well. Okay. So I make a note, and then you run the route design. So route design, first you run route without make sure everything is clean. So you can each step you already analyze your congestion and all to make sure by this time when you run a route, you have a clean route. And even though you do timing report here, but expect it to be timing be messed up, because during this time it does very minimum the timing fixes. So that's the job of timing route optimization, where you run the route opt command and you iterate on violations to this design properly, very easy to fix timing during route optimization. But you still run these things and do a timing report at the end. These timing reports better be clean, meaning everything is clean by this time. And then you run chip finishing, you will learn what these steps are, but you haven't been taught yet. So I will leave that until later. So as you go through the steps that you already learned, you have a lot of questions already, and then you'll run the chip finishing and export the design. Tien will teach you later. So at the end, we'll worry about this later, but at the end so you run everything in your run directory, but we want you to copy things into something called final, and that includes the final database, include the report, all the reports, and you run something called quality of the result report. We'll worry about this later, but it will show you the floor plan, including the placement of macros. I blanked this out because I don't want to give your suggestion of where the macros are, but you will see we'll look at this location of macros, and you see the timing the timing report on different stages, right? Place, CCS, and all. What are the setup and hold time? So you better not having any red here. So you're gonna be fixing all the worst negative slack for setup and hold, and there are informational clocks and power, etc. So at the end, you run report timing, post route, and you report power, and you report the areas. And like I mentioned, we are working on submission form, which is similar to the pre-assessment. But you see, this is a form that help us grade and then look at different results easier and help us create the result better. And then when this is optional, when you have extra time, you can increase the frequency, the V clock 1, which is the main system clock. So you maintain the same floor plan, but you increase the frequency until you cannot increase anymore. And then, or you can keep the frequency originally, but you squeeze the area, meaning the core density. So you start shrinking the core, and you find it's path limited, meaning you can shrink the core, but the space from the core to the IO might increase from 100 to more, because you cannot shrink the IO anymore. But you can do it so at the end you might have the same speed but smaller design. Those are the actual candidates. So okay, I think that's it for now. And if you have questions, then talk to your TAs, and we can address them next week on Tuesday.
And I think somebody, one student asked to see how to select a macro.
Okay, you want to
Okay.
answer that?
I'll show you how to select, for example. Let me share it real quick so they can note this down. Okay, should you see my screen now? So, for example, let's say you want to let's get the DB first, right? So remember, we know the name of the DB, right? And you can select, just do a select OBJ's object, and you can pipe that into this command here, right? And you will see the PLL will get selected right here. As you got highlighted. Okay, so you can pipe any command into any command. So select and then get instant DB. So basically, let's say select this object, the instance. So a graph. You can do the same thing with the RAM also. Okay, so that's how you select your script, and you select it, and then you start running till you add ring command, and then you'll add a ring around this guy. Okay.
All right, I am reading Võ Thế Dũng question 10. Did we answer them correct? Do we need to say more about his question?
Yeah, very much. Yeah, he asking about for the summary, so I answer him essentially. Make use of the cadence help, right? So this should have everything he needs.
Yeah. So you do review the materials we cover, and like I mentioned, there's no way we can review everything with the amount of time we have. And so, but the burden is on you to review the materials and come up with questions on things that you don't know the answer for. But please try hard to read up. And I gave you the user guide, command conference guide. So a lot of these things are self-learning, right? So you have a ton of information to review. So please do spend time on searching for the answers. But if at the end you don't find the answers from the documentation and from your TAs, please bring it to the class. We only answer questions. We don't want to review and reteach everything. Okay. All right. I think we're 2 minutes over. So, Tian, you have the last words.
No, thank you, Phil and Bat. Yeah, I think actually now, because we have say, is that 2 more weeks before they turn in the project?
Yeah, 5/19, and there are some concerns about lack of time. We could consider postponing, but we prefer not to. Please try your best and see if you can. I know you're busy, but if you can meet the timeline, it'll be great. If not, then we'll see how it goes the next couple of weeks. But please thought on them and see how it goes. Okay.
Yeah, I think for the student, it's good to start early, right? And then see what you're missing. Yeah,
Yeah, I think
you don't
start
want to
early.
wait for the last minute. Yeah.
Yeah, start early so that you can come to class the next session, ask question, and then the next session there's more time, and then also during the open the tutorial session. That way you will help you whatever roadblock you have, we can help you get over it, and then you can move on.
Yeah, the last class will be just for very, very urgent need, so we can have breakout rooms and all. Just this is the last time, but that's the 17th. So you have 2 days after that. So if you sign up, maybe for last minute, you want to sign up a lot after 17, 18, and 19. So you have things at the very tough questions to ask, and the last session will be the place. But do ask questions early so that you have enough time to complete before the last week.
Okay.
Right. I think everything in the lab we have covered in the lecture, right? So there's nothing really new, right? Except for the extra credit, right? Everything else is, yeah. If they go through the lecture and the lab so far, you should be able to do all of that.
Yep. So hope to hear the questions next Tuesday. Okay.
All right. All right. Thank you, everyone. See you next Tuesday.
Bye. See you next week. Have a good weekend.
Okay. Bye-bye.
The recording has stopped.